Hello everyone, I'm Sri Ganeshan and today I'm going to talk about moment of inertia. So let's get started. Here's an interesting experiment for you. I have with me a solid cylinder and a hollow cylinder. If I place them at a particular height in an inclined plane, which one do you think will reach the bottom first as they roll down? Well, let's see. We see that the solid cylinder rolled down and reached the bottom first. Why do you think this happened? Let's take a look. Consider the cross-sectional view of the cylinders. Let MH and RH be the mass and radius of hollow cylinder. Similarly, let MS and RS be the mass and radius of solid cylinder. The axis of rotation is a line passing through the center and perpendicular to cross-section of the cylinders. In our experiment, the cylinders undergo rolling motion, which is a combination of translational motion and rotational motion. So we can break our analysis into two parts, translatory part and rotational part. So when the cylinders reach the bottom of the plank, they will have an angular velocity omega h and omega s due to rotation and linear velocity vth and vts due to translation. Now, consider the cross section of a hollow cylinder. Let us break this ring into small chunks of mass as shown here, with each chunk having a mass of dm such that summation over all dm gives mh, the total mass of hollow cylinder. Now consider just two mass chunks which are situated diametrically opposite to each other as shown here. Each chunk has a linear translational speed Vth and a tangential speed Vrh given by the radius times the angular speed as shown in this figure. Clearly, these two vectors have opposite direction. The net velocity of each mass chunks can be derived using parallelogram law of vector addition. Let Vh1 and Vh2 represent the net velocity vectors of these mass chunks as shown here. Then, the square of their magnitude can be calculated from using this formula, which can be derived using the parallelogram law of vector addition. Using this, we get the following two results. Note that these two terms have opposite signs, so when I add this and this, I get only 2 times Vth square plus Rh square omega h square. Now, the total kinetic energy of these two chunks is the sum of the individual kinetic energies, which is nothing but half dm Vh1 square plus half dm Vh2 square. Clearly, when I substitute the expression in this equation, I get half times 2 dm Vth square plus half times 2 dm Rh square omega h square. Let's call 2 dm as dm dash. Now, the final equation becomes half dm dash Vth square plus half dm dash Rh square omega h square. Now, let us look closely into this equation. Clearly, here this part is due to the translatory motion, so this is called as the translational kinetic energy, and the second part, which is due to rotation, is called the rotational kinetic energy. We know that angular speed is the rotational analog of linear speed. So by comparing these terms, we can conclude that dm dash r square must be the rotational analog of mass dm dash. This term is called as the moment of inertia of this system about the given axis of rotation. Note that moment of inertia not only depends on the mass dm dash but also on the position of the mass chunks with respect to the axis of rotation. More specifically, it is directly proportional to the square of the separation between the axis of rotation and the mass chunks. Therefore, it is very important to specify the axis of rotation when calculating the moment of inertia of an object. Now, to find the total kinetic energy of the entire hollow cylinder, we just need to sum up the kinetic energies of the individual mass chunks. Therefore, total kinetic energy of hollow cylinder is equal to half times summation dm dash Vth square plus half times summation dm dash r square omega h square. If we make the mass chunks infinitesimally small, we can replace the summation by integrals and we get total kinetic energy of hollow cylinder is equal to half times integral 0 to mh by 2 dm dash Vth square plus half times integral 0 to mh by 2 r square dm dash omega h square. We can write this integral in terms of dm by changing the limits to 0 to mh and we get half times integral 0 to mh dm Vth square plus half times integral 0 to mh r square dm omega h square. Therefore, the total kinetic energy of hollow cylinder becomes half times mh Vth square plus half times ih omega h square, where ih is equal to total moment of inertia of the hollow cylinder about the given axis of rotation. If we compute this integral, we get ih is equal to mh rh square. Substituting this, we get kinetic energy of hollow cylinder is equal to half times mh Vth square plus half times mh rh square omega h square. We can generalize this procedure to calculate the moment of inertia for any object. First, break the object into small chunks of mass dm such that summation over all dm is equal to mass of the object. Then find the moment of inertia of each mass chunk with respect to the given axis of rotation. Call this di, which is equal to r square dm, where r is the distance of the mass chunk from the axis of rotation. The total moment of inertia can then be calculated by summing up the moment of inertia of individual mass chunks. So for discrete mass distributions, we will have the total moment of inertia is equal to summation of 0 to mass of the object r square dm, and for continuous mass distribution we can replace the summation by an integral, and we have total moment of inertia of the object is equal to integral 0 to mass of the object r square dm. Note that in order to compute this summation or integrals, it is important to specify the axis of rotations. So, if you choose a different axis of rotation, the moment of inertia about that axis may be different. Using this procedure, we can calculate the moment of inertia of the solid cylinder. So, the first step is to break the cylinder into small chunks of mass like this. Note that in this case, there are mass chunks located closer to the axis of rotation. As a result, the moment of inertia of the mass chunks closer to the axis will be less than the moment of inertia of mass chunks further from the axis. We can see this if we consider these two mass chunks. This mass chunk has moment of inertia di1 equal to r1 square dm, and this has di2 equal to r2 square dm. Clearly, di2 is greater than di1 because r2 is greater than r1. Continuing our procedure, to calculate the total moment of inertia, we need to sum up the moment of inertias of all the mass chunks. Since our cylinder has continuous mass distribution, we can use integration to calculate the total moment of inertia. If we compute this integral, we get the result as Is is equal to half ms rs square. Let's first hold on for a moment and compare this result with that of the hollow cylinder. We have I hollow is equal to mh rs square, and moment of inertia of solid cylinder is equal to half ms rs square. Just for the sake of understanding, for a moment, if we consider mh is equal to ms and rh is equal to rs, then we see that moment of inertia of hollow cylinder is greater than moment of inertia of solid cylinder. Does this make sense? Of course it does. First of all, in the two cases, there is a clear difference in the way in which the mass is distributed around the axis of rotation. So for the solid cylinder, majority of the mass is distributed closer to the axis of rotation as compared to hollow cylinder, and since moment of inertia depends on square of the distance between the mass chunks and the axis of rotation, we can therefore expect that total moment of inertia of hollow cylinder is greater than total moment of inertia of solid cylinder, and this is exactly what we get when we compute the integral. Therefore, this result does make sense. Now, coming back to our experiment, our solid cylinder also undergoes rolling motion. So as it reaches the bottom of the plank, it will have a total kinetic energy given by half ms vts square plus half is omega s square. Here, this is the translational kinetic energy and this is the rotational kinetic energy. Substituting for is, we get total kinetic energy is equal to half ms vts square plus 1 by 4 ms rs square omega s square. Now, so far we have the following two results. Let us apply the law of conservation of energy. Initially, both the cylinders are kept at a height h on an inclined plane. Hence, they will possess an initial potential energy given by mh/gh and ms/gh. As they roll down and reach the bottom, all of this potential energy gets converted to kinetic energy. So we have the following two equations. After simplifying this equation, that is by cancelling out the mass components, we get gh is equal to half vth square plus half rh square omega h square. Similarly, gh is equal to half vts square plus 1 by 4 rs square omega s square. Our cylinders in the experiment undergo purely rolling motion. For pure rolling motion, the following condition must be satisfied. There should not be any relative velocity between the point of contact and the surface. This means that its net velocity should be 0. This implies V should be equal to R omega. If this is not true, the cylinders will slide. Imposing this condition on our cylinders, we get Vth is equal to Rh omega h and Vts is equal to Rs omega s. Substituting this relation in this equation, we get GH is equal to VTH square and GH is equal to 3 by 4 VTS square. So finally, we get the following result. GH is equal to VTH square is equal to 3 by 4 VTS square, or VTH is equal to root 3 by 2 VTS, or in other words, VTS must be greater than VTH, which is what we observed in our experiment. The reason we observe this is because the mass chunks present far from the axis of rotation consume greater amount of energy to rotate with a given angular speed compared to those mass chunks situated closer to the axis of rotation. Since in hollow cylinder, all the mass is concentrated far from the axis, it consumes greater fraction of initial potential energy to rotate as compared to the solid cylinder. This is because of the moment of inertia term present in the relation for rotational kinetic energy. I hope after watching this video you have gained more insight into the concept of moment of inertia. Thank you for your attention. See you next time.